Hello, welcome to my YouTube series. This YouTube series is going to be It's going to be a three-part YouTube series covering topics all related to Connect 4 neural nets. This video here is going to be demonstrating the techniques I used to train neural nets using the input board data and mapping that to output data generated by a Minimax algorithm and training the neural nets to emulate the Minimax algorithm. The second video is going to be is based on self-play techniques. That whole process was based on the AlphaGo project by Google, in which they were able to train their AlphaGo agent to play Go at a superhuman level by continuously using self-play to develop this really intelligent neural net that is now basically unbeatable at a human level. Mine's obviously not nearly that good, and Connect 4 is solved anyway, so it doesn't really matter. But it was more about using those techniques to continuously train neural nets to get better and better. And we'll take a look at how the neural nets are able to use the stored data from earlier games to improve themselves, and how the champion is continuously chosen. The last video is going to be about just integrating neural nets with the Django website, letting the user sort of interact with and do a couple different things, but they can upload their own neural net, and they can hold like large-scale tournaments of, say, 5 games or 10 games or however many games you want between 2 different neural nets. They can also play against them themselves and kind of play around with it that way. It's just sort of a playground. The first 2 videos are probably a little more complex. But anyway, so to get started, this is the folder for the whole project. We're only going to be working with a couple of these files today in this video. Those would probably be the engine file, the Minimax file, the NN functions file, and this NN file. So this engine file contains sort of the rules for Connect 4 built using Python. By the way, we're using this project uses Python and it uses the TensorFlow library for the neural nets. I chose TensorFlow just because it's a very good beginner library. There's a lot of community support, which is always great when you're learning, and it's very powerful as well. So I was able to, I found it a pretty smooth process for this project. So we have the engine, which contains the rules for Connect 4. We have the Minimax, which is used to generate both moves and to assign a value to a certain board. I'll explain what that's used for later on. We have the NN functions. This sort of handles what we're going to be looking at in there is how the input board data is served to the neural nets, how we change the board data as it's used in the engine file to how it is so that a neural net can read it in a useful way. And then finally the NN file, that's the file that I used to actually finally generate the neural nets. Let's hop in here to the engine file. We're just going to take a quick tour through here and look at how the Connect 4 stuff actually works. We're just this is meant as kind of an overview. We're not going to get super into the detail because this is really the base of this video is all about training neural nets, not really about Connect 4. But you need to understand what some of the data looks like that's being held to understand how it's actually being converted. So the data for Connect 4, the board is held in this board class, and then we have this board attribute here, which turns into a double array. There's the first layer, and then it's filled with these row layers, and then each row is filled with these cells. These cells are this class here. Each cell has 2 attributes, is filled and is read. These are both booleans. So the is filled indicates whether the cell is empty or not, and then in the case where it is not empty, the is read is true or false, saying if it's red. So if it's true, then the cell then it represents a red tile, and if it's false, then it represents a yellow tile. Pretty straightforward. So this is the function that either initializes from a blank board, or you can also build it from an existing board, which was useful in some cases where you needed to create a duplicate of a board. So we have a couple other functions here that are important. The serve next state function was a very central one. So what this does is it's how the game actually advances. You have a board, and then you pass a column number, and you pass the is red. This indicates whether it's the red or the yellow player playing. what it does is it takes the column number and scrolls through there, and eventually it'll either hit the bottom in the case where the column has not been played at all, or it will hit a filled cell. And what it does in that case is it'll set the cell above that one to is filled, and it will set the is red attribute to either true if it is red's turn, which you assume has been correctly passed here, or false if it's yellow's turn. It's the most important thing that does. In here we also have a check win function, which checks, so you pass a coordinate, both a row and a column for the cell that was just played. And what it does is it'll check for the horizontal win, vertical win, diagonal, ascending, and descending wins using these functions here. This is the stuff that I don't want to get into because it's kind of just like very tedious. If you're really interested and you want to see how the Connect 4 game was actually built, there's going to be a GitHub link, and you can go and you can comb through it and check every line if you want, and make sure I'm being honest here. With that, I think that's all I want to look at here. There's a check draw function. This one's pretty simple. It just looks at the top row and sees if everything is filled. If everything is filled, then that means on the top row, that means that all the rest of the cells have been filled, and that means that the game is over, given that the end is a draw if the check win function hasn't returned a true value. So that's all I want to look at here. I just want to do a quick example. So here's a CMD that is running in the folder. So I just want to put engine. Okay, so now we're in that function here, and we can see this is the output of this printboard function here. So it goes through each row, and then for each row it outputs this underscore here for a blank line. It outputs an X for a red piece and a yellow for a yellow, and a circle for a yellow piece. So we can see here, I said column 1, this is a 0 index list, so if I put in 0 here, then that's actually the first column. We're just going to do a really quick game here, where red's going to win quick. The game was won by red. Right. So we can see that there is a kind of a working Connect 4 that's like logically putting the pieces in the correct spot, and it's running, and it's correctly detecting when the game has been won. I'm just going to quit out of that now. So what I want to move on to next is we're going to be looking at how the neural nets, how we generated our data to train our neural nets. The first thing I'm going to explain is the input data. So this is how the actual board state gets fed to the neural net, because you can't just feed it in the raw kind of state that we have here with cells. You want to perform some kind of process on that to make it the neural nets be able to interpret that a little more clear, like what the state of the board actually is. So that is happening in this function here, the board to inputs function. Once again, we have a board array, and it's going to be filled with row arrays, and these row arrays are going to be filled with, instead of cells, so this takes a board from the engine as an input, but instead of filling it with cells, it's turning these cells into these miniature arrays here. Because there are three distinct values that a tile can have. A tile can either be empty, or it can be red, or it can be yellow. That's what each of these represents. So we have, if the cell is filled here, the else means that it's not filled, so that's a 1, 0, 0. And then here, this is a logical thing that I did to so that this function can be used both during red and yellow turns. So you pass the turn that it currently is, and then it identifies, it takes that variable and uses it to identify if it's either a friendly cell or an enemy cell. If it's either the cell, if the color of the tile is the current player's turn, if it matches the tile that the current player is going to place, or if it doesn't. So that was a way to just make that sort of agnostic, and it was thinking in terms of friendly cells rather than red and yellow cells, which could have changed the way the board interacts. You want your neural net to look at to be able to work for both yellow and red players, and not see differences between red and yellow squares. You want it to see friendly and enemy squares, so it works the same no matter which color it's actually playing. But the final data that we'd get here would look like, so you can imagine a 2D array of these that is, oh god, that is filled with these, instead of instead of cells. The reason that I did this, so in a case like this where these aren't scalar values, they're like distinct categorical values. So what I mean by that is, alternatively, we could have had an empty cell being 0 and red being 1 and yellow being 2, but that sort of implies that red is somehow in between an empty and yellow state, which isn't true. They're 3 independent states, and they're not on a scale. They're just like 3 different things. So that's why this vector sort of representation was implemented. Supposedly, this helps neural nets learn a little bit better. So I went with that. Next, I want to talk about the Minimax algorithm. So that's the input that we're giving our neural net when we do train it. The Minimax is used to generate the output. So what we have here is so a Minimax algorithm, I just want to give a quick overview. A Minimax algorithm is an AI algorithm that's used in turn-based games, usually in turn-based games where there's like high enough complexity that you can't simulate it all the way to the end. So Connect 4 has like middle complexity. It's not as complex as like chess or Go, but it's a lot more complex than tic-tac-toe or, I don't know, flipping a coin or something. And not that that would really work, but for this scenario, but I thought it was a good middle ground, and that's kind of why I've based a couple projects off it. I have another project in the past where I built a Minimax algorithm, and this project was kind of an evolution of that, and just to take it a lot further and implement neural nets and see where I could get with that. So what a Minimax algorithm does is you set it a certain depth, and that is kind of how far ahead the Minimax algorithm is going to be looking. So if you set the depth to 1, the Minimax algorithm looks at all the moves that are 1 turn ahead. So in Connect 4, if none of the columns are filled, you have 7 available moves. So it would simulate 7 boards and apply its heuristic function. The heuristic function is used to generate a value for that board. So the heuristic is usually a way to rank boards, and a board that you think that the heuristic function believes is likely to result in a win for that player would be given a high score, and then one that would be likely to result in a win for the opponent would be given a low score. When it gets a little more complicated is when you set the depth a little higher. So if you set the depth to 4 or whatever, it goes, which I think I put it usually on 4 or 5. I think was usually a good trade-off in terms of performance, versus you want it as high as possible without it slowing your program down too much. So it was in that range. So it looks that far ahead and starts simulating those boards, and then it eventually gets to a spot where it can start pruning entire sort of branches of that tree. So if you imagine it as your first layer of 7 boards, and then each of those has 7 children, provided that none of the columns are filled. So it's actually increasing exponentially very fast, but it can prune large parts of it when it figures out, my opponent gets a good move if I do this, so I don't even need to look at the rest of those, because I already know that this branch can give me a better result than this branch, and it uses that to like cut large portions of the tree that it's simulating and save on computational time. So that's an overview. Once again, this video isn't about Minimax algorithms or even really about Connect 4. It's what I want this video to be about is about training neural nets on something, in which in this case is Connect 4. The Minimax comes in because it's generating our output data. We're matching that input board state to 2 different things. We're matching it to either a move that is chosen by the Minimax algorithm. So the Minimax algorithm would finally set a score. The score is kind of back propagated up, and then the maximum node can be chosen by the Minimax algorithm as like the best move according to that heuristic and according to the logic that it's been programmed with. So it's used to output a column number given a certain board, and then it's also used, I have a function somewhere in here, gen game results, where it'll take a board and then it will play using its Minimax algorithm, and play it until the end, and then it returns one of 3 values. If it's a win for the player, then it will return a 1. If it's a loss, excuse me. If it's a loss for that player, it returns a -1, and if it's a draw, it returns a 0. Here's the getMove function. So this is the one that's used to generate the move choice given a certain board. It's turned out to be a one-liner, even though it's kind of confusing to look at. But basically what we have here is once the tree's been generated, it gets the scores, and then it chooses, this is useful in the case where there are 2 scores that are the same. So let's say there's a tie, and then it'll choose one of those randomly. So that introduces a little bit of a variance. That means that, it doesn't always make the same move in the same circumstance. If it says that 2 paths are equally good, it'll choose one randomly. And then it also has to be present in the legal moves for it to be returned in the end. The reason that we have this, I developed this later on in the project because the AlphaGo uses value and policy networks. When it's so the value network is sort of an estimation of how strong a board is. It's like a neural network performing the role of a heuristic function, and then a policy network is one that chooses this move is this likely to occur in this scenario, and sort of rank each of the moves that are available, like rank them according to how good it thinks that they are. So those are the 2 neural nets that we're gonna try and make, and these are the functions that are used to generate the output data for them. So an analogy that I'd like to make at this point is a lot of people who study neural nets are familiar with the MNIST example, in which handwritten digits, images of handwritten digits are input into a program and mapped. So you'll have a map of the handwritten digits and the actual values that were intended to be written, and then a neural net will be trained on that, and then it will be able to identify other handwritten digits that it hasn't seen before. So in this analogy, our input is the boards, and our output is the moves that are being made, and also the value, whether it's a win or a loss or a draw. That's what our neural nets are going to be trained on. So I think without further ado, we can I think we might be able to get started and make our own, make a new neural net here. This is the function that I used for that, or sorry, the file that I used at the start when I was making the first neural nets in this project. There's a few config values here that you can use to change the neural net that you're making. So you can see here this argument is input into this map, which returns a function. Eventually, it returns one of the functions that we saw here. Make simple model, and so these are 2 kind of arbitrary models that were made at the start using the TensorFlow library. If I didn't mention earlier, we're going to be using the TensorFlow library in this project. That was chosen just because there's a large community around it, and that's which is always great if you're starting out by yourself and you want to learn whatever it is. So and it's very powerful, and there's a pretty good documentation for it as well. So that's what I settled on for this project. Anyway. So we can look at one of these. What I want to focus on as well is how the how the output data actually gets generated here. So what I have is, because mapping your data from the input to output, usually you want quite a lot of examples here. This is the example argument that I have, and generating 1,000 can actually take quite a significant amount of time. So what I did is I used the pickle library. Pickle library is a way to save serialized data, and it's going to load that automatically and use that to train a new neural net. But in the case where you might say that 1,000 is not enough and bump that up by a significant amount, it'll actually generate all that data. We can do that later and actually look at some of the data being generated. So let's go ahead and generate, so the arguments here are control what network actually gets generated in the end. So you can see here we're generating a simple policy network, and then this is going to be the eventual eventual title of it. So because it's a policy network, that means that it's choosing a column. It's outputting a move. So if we look at the map that we get, you can see that it maps to a get move function that we saw earlier in the Minimax file. Because there's 7 columns, there's 7 moves. Because there's more than one category, we're going to use the categorical cross entropy argument, and then this here is used to title. Is used to either find the existing pickle data or title the pickle data that's generated, in the case where you're generating your data for the first time. Okay, so let's go ahead. So also I have a debugger point here, so we're going to walk through it. That's where we should hit. So .py. Here we are at this line here. So that's the model being made for the first time. I also like to take a look at so the ret data is so we can take a look at our boards. These are the input boards, I believe. So you can see that it's not giving us the cells. It's giving us that categorical vector representation of the cells. So you can see that this is a red cell, and then that's and that is a a lot of these cells are filled in this one. These cells are unfilled. And then I also want to take a look at the ret data. So the ret data is the data that was given to us, and the data in here is coming back in this format. So what this means is, so the data was passed back as a value from an integer value 0 through 6. It was either 0 or 1 or 2 or 3 or 4 or 5 or 6. But at when you were generating that data, it actually transferred. There's this function called toCategorical, which breaks that up into these vectors. So a 0 would be represented by this vector here. A 1 would be represented by this vector here. Meaning that a 1 is the value of the 0 index of that array. In the case where the value is 0, if that makes sense. So this one is it's not a 0, it's not a 1, it's a 2, and so forth. So this is the data that's being input to our sorry, just going back to this function. This is the data that our model is going to be trained on. So we can go. Oops. So this is our model initialize function. This is where it makes the simple model. I'm inputting a board shape, and then the function output set. So what is that from? Our function output set comes from our function output map, and it's going to be generating moves for each of those. Or excuse me, why is it generating moves? Function output set. Oh, function output set 1. Sorry, 7. Yeah, so that's the amount of categories that it will come out with in the end. Okay, so let's just step through. Okay, so if you guys have used TensorFlow library before, some of this will seem familiar. You can see that we had 1,000 samples, and we chose 3 epochs to train it on. Here's a summary of the neural network shape that was output, and then I think that I have some sample data here at the end. But what I want to look at is, what we can look at here is this stuff. So the initial accuracy is not great, but we can see that it on the second pass it is able to improve quite a bit, which could indicate probably overfitting if it's just like learning that data really well. It's hard to say. You need to train it on new data. Which does that happen in the end? I believe that this is new data in the end, because after that function we get a ret data test. Where are you coming from? Right. So here it's looking for test data using that, and it actually gets a 41% accuracy. So if you think about the accuracy of randomly choosing the correct move is 1/7. So that's what, like a kind of around like 13%. So it's choosing the right move 41% of the time, which is pretty good, I think, for what's a simple for what's a simple neural net with only 1,000 input training boards. And then finally here, what do we have at the end? It's probably good to explain. So this is the output of the probabilities. What lines are we looking at here? We're looking at these. So I think that these are some, I wanted to contrast sort of the probabilities that are being generated here with the actual matching data from the ret data test. So you can see here, like, so the third column was the correct choice, and here it's giving 3% to the first column, 3% to the second column, and then 12.5% to the third column, which is the best there, which is so great. Anyway, that's one simple neural net. We can take a look and make another. Why don't we make a convolutional neural net and take a look at, actually, no, one thing that I'd like to do is let's generate our own data. So we can generate, I don't believe that I have a value for, let's just say 50 might be a good amount, because I don't want this to run too long. And we can take a look at how the scores change. So this will be a neural net that is trained on only just 50 samples 3 times, and we'll see how accurate that gets. Oh. So it only got to 22%, so not a dramatic increase at all, but we can get a sense there of, also, we saw here, this is when it was actually generating the samples itself on the back end, and it did that pretty quick. So maybe 1,000 wouldn't have been that bad after all. When I originally did this project, I was working on my laptop. Now I'm back on my desktop, which is, I guess, more powerful. So do I want to end the video there, or do we want to do a convolution? That's everything that I want to show in a nutshell for this video. Let's also do a convolutional one. It's been a while since I've used this, so I'm not 100% sure it's going to work. But we'll see how that works, and we'll use the same data as before, because I don't want to spend a long time looking at stuff loading. So this will grab the same sample data as we had before, and we'll see how the convolutional network performs in comparison to the simple network. Should probably take that. Right, so I think this one takes a little longer to train, as the convolutional network has more of a complex structure to it. We can take a look at what the convolutional network actually looks like here. It has these convolutional 2D layers. Once again, this isn't a video about what a convolutional network actually is. That's something that, if you're interested, you should look up on your own, but it's good for 2D representations of objects. If you've looked at the MNIST database stuff, then you might have heard that term before. But I decided it would be interesting to see how that contrasts with the accuracy that we're getting here. And so the accuracy is, unfortunately, I think the exact same, right? Wasn't the neural net giving us 41% as well? But it's nice to know that the convolutional networks are at least viable. I know that in the AlphaGo project they did use convolutional neural networks. So it's a way of looking at groups of, looking at chunks of the board, and kind of looking at those chunks a little bit individually, and that sort of decides what your actions are going to be, rather than just like looking at the cells individually. That's a whole other topic to look into, but I think that covers what I want to cover for today. So thanks for watching. If you have any comments or questions, definitely let me know. And yeah, thanks.